What's up everybody, Mr. Gill here, back with another video, this time focusing on chapter 6, called Molar Heat. But before we even get into that, I want you to take a look and think back at what we've done so far. Alright, now for chapter 4, we focus on two different ways to find the energy released or absorbed by a process. The first one was, if you were given a chemical reaction, we used the bond energy table to figure out the bonds in each of the reactants and each of the products, and we estimated the enthalpy change. That was method 1 in chapter 4. Now method 2 was, if you were given the reaction and you were given the enthalpy change of the reaction, you could use your ratios or stoichiometry to figure out how much energy was released or absorbed. These two are your tools so far for your end term test that you could use to figure out how much energy was released or absorbed by a reaction. Now, you may have also noticed in some of the challenge questions or in some of the questions that were just very difficult, especially like your millionaire game, the $1 million question, involved using maybe a calorimeter or using a reaction to heat up a substance. Now, you may be thinking, sir, why did we do that? Why would you make us go through that? Well, because you're going to see the use of a calorimeter or using a reaction to heat up a substance is exactly what molar heat is about. So it was a preparation for you to start thinking about the energy transfer that happens between a reaction and another substance that is around or the surroundings. So let's get into it. The first thing is first here. What is molar heat? Now, molar heat is the energy released or absorbed by a process or a reaction for every 1 mole of reactant that you use. Now, I cannot stress this enough. It's the energy released or absorbed by 1 mole. 1 mole, 1 mole. So please bold that, put a star in your notes. It's very important. It's the energy released or absorbed by 1 mole of reactant that you use. Now, how do we do that? Well, we've already seen the calorimeter, so you already have an idea of what it is. Now, just to remind you what a calorimeter is, it's just a vessel which is assumed to be an isolated system, and the idea is that the process happens, and when the process happens, it changes the temperature of the water around it. Right. What process are we talking about today? Well, we're looking at first the molar heat of dissolution, and dissolution is the process of dissolving solute into solvent. More specifically, it's the heat absorbed when you dissolve 1 mole of solute into solvent. Now, the other picture you saw was a little more complicated. It was more for industries because you don't really have a steel chamber and stuff like that. This is the one that you're more used to from the lab that you did, the energy transfer lab. You could use the styrofoam cup as your calorimeter. You assume that because it has a cap on it and it's made out of styrofoam that there's no energy lost in exchange with the environment. So the idea here is that if you were to dissolve solute, so like a salt, into water, when the salt dissolves into water, energy will either be released or absorbed due to the reaction, and that will change the temperature of the water, and we can record this. Okay, so let's take an example here, just to, again, get the ideas thinking, do a little bit of analysis so you can understand the method. Again, you've got now this salt, ammonium nitrate, which requires 25.7 kilojoules to dissolve into water. Now this dissolution absorbs energy because you could see the enthalpy or the energies on the reactant side. It needs that energy to dissolve. So if the reaction needs energy to dissolve, where is it going to get that energy? From the water around. So once the salt goes into the water, it will steal 25.7 kilojoules from the water, which will cause the temperature of the water to go down. And now since we know, or since we're assuming a calorimeter is an isolated system, whatever energy the reaction absorbed, the water will lose. Right? Now that's a simple analysis for this case. But what we could do, just like we did in the energy transfer lab, is we can actually measure the temperature change. We can go backwards. We can measure the temperature change, and therefore we could figure out the energy the water absorbed or released, and therefore figure out what energy the process absorbed or released. And that's exactly what we're going to do here. And here's an example for you. So the question says we dissolve 14 grams of copper sulfate into 300 grams of water. The temperature of the water rose from 14 degrees to 17 degrees. What is the molar heat of dissolution for copper sulfate? Okay, so we again do the same analysis. If the temperature of the water goes up, that means that the dissolving of copper sulfate into the water released that energy, because whatever energy was released by that dissolving process heated up the water. Because we know everything about the water, we're going to start there. We know the temperature of the water went from 14 to 17 degrees, so that's a change of 3 degrees. We know the mass is 300, and we know the specific heat capacity of water is 4.19. So we can calculate how much energy the water absorbed. The water absorbed about 3,771 joules. Step 2. Well, where did that energy come from? It came from the dissolving process. So the process must have released 3,771 joules. Now remember, the molar heat of dissolution was the energy released or absorbed by a process for every 1 mole of reactant. So in our question, if you go back, we had 14 grams of copper sulfate. How many moles is that? Well, let's figure that out. So if you look at the molecular weight of copper sulfate, which is about 160 grams per mole, we had 14 grams. So we have about 0.0875 moles of copper sulfate. So our process released 3,771 joules of energy, but that took 0.0875 moles to do. And we said the molar heat of dissolution was how much energy is released by 1 mole. So you can either do a ratio for yourself to figure out the answer, or you could do an easier approach like this. You can just simply divide the energy released by the number of moles. And that will get you your molar heat of dissolution. Now, if you do the math, you'll see that you get about negative 43,000 joules per mole. These numbers are going to be generally very high, so we're going to, most of the time, convert joules per mole to actually kilojoules per mole to make the numbers a bit easier to work with. And that, in fact, most of the values, if I give you the enthalpy change, will be in kilojoules per mole. Just a note here that if you look at the subscript for D, we did find the enthalpy change. That is our molar heat. But the thing is, we're putting an extra subscript D there to denote that this is a dissolution. You're going to see in the next video that we have a different process. So we're just trying to be clear that this is a dissolution process, so that's why we put the D as a subscript. Now, that's pretty much all there was to it. And so you can have a little summary here, follow all the steps that we just did. So step 1 was determine the heat that was absorbed or released by the water, which can immediately tell us what the the dissolution did, because whatever energy was released by the dissolution went to the water. Now that you have the energy of the reaction, you just got to divide it by the number of moles of solute. So solute was the thing that we dissolved, which was the copper sulfate, and that gets you your molar heat of dissolution. That's all there is to it. So give this example a try. I give you the answer there. Not too bad, and you can check out the second video.